Problem situation. Hi, my name is Luis Ricardo Navarrete Cadena, and in this presentation, we'll explain the problem situation. Introduction to the problem. With a motivation, the need for automatic control. The problem involves a non-isothermic reaction that will be analyzed. An exothermic reaction occurs here. The reaction is described as 2A equals B. The variables that are controllable are the flow of A and the coolant through the cooling jacket. This problem needs automatization for controlling the flows of the the feed and the coolant, because if the flow of the reactant is too great, a lot of heat will be generated, causing a rise on the pressure inside the reactor. And if the cooling jacket cannot cool the reaction, then the same problem will appear. It is important to note that after an energy and mass balance, the following equation came as a result: XA, XT, and XE. The model A1 will be used from now on for the following calculations, starting by the equilibrium calculation. What is equilibrium? Equilibrium is a condition in the course of a chemical reaction in which no net change in the amounts of reactant and products occurs. With the simulation, it can be seen the chemical equilibrium in the system, setting all the signals in constants. O1 equals 0.5. At equilibrium in model 1 will be given by the following: XA0 equals 0.531, XT0 equals 1.139, XC0 equals 0.926. Now, we have to first put a step on the system in the simulation. In the simulation that has been given to us, the north had been in this plus sign. You have to change that to a negative sign. Then we demonstrate a simulation to demonstrate the equilibrium. We plot the graph, the concentration of the A reactant, and it can be seen that is 0.531. On this graph, it can be seen clearly that the concentration starts at a high value and then it decreases. This is due to the start of the reaction. Since it has started, the concentration decreases. Afterwards, the concentration should increase. In the graph, it decreases because of the change on the sum nut that I have told you before. It will be an increase again since the speed of reaction is no longer being favorized by temperature. As we know, more temperature, it will increase the reaction. Finally, we can see the verification of the final value at the equilibrium of the temperature. This will be shown on the graph below. You can see again, it decreases, increases, and then it decreases in equilibrium. It can be seen clearly that the value at the equilibrium is 0.926. Then it arrives at equilibrium because of the constant temperature at the tank. Explanation for the method used for fitting models to the response of the plant. A PI controller helps in reducing both the rise time and the steady state errors of the system, to be useful wherever you need to change magnitude and lag the phase together. A PD controller reduces the transient like rise time, overshoots, and oscillations in the output. In a PD controller, you can see that D is for dampening, and this D is used in overshoot and oscillations. The method that was used in this problem was a PI design because it was the best to use in second order system. The system was used in the lab and has proven to do well in this case of system. The design method we use a simulation. First, we have to calculate tau and theta. The function is modeling the step, the step that we say before in the 3-4 presentations. You can see that the step is 0.2 and extra. We can see that the graph starts at 1.139, therefore YF will be 0.025, and we know that this distance between the reference value and the step UF is 0.2. We said it. Therefore, for the calculation of the gain, the following formula will be used. K equals YF. divided by UF, where at the moment of substituting K equals 0.025 divided 0.2 equals 0.125. It's known that the equation that models this graph will be the next. GS and K is to the value of S theta divided by S tau plus 1. For the obtaining values of theta and theta, of tau and theta, we need the values of T1 and T2. With the following formula, 0.283 multiplied by YF plus 1.139 equals Y1. And then we do this again with Y2. You can see this in the graph that the value of Y1 is 1.146, although the value 1.1464 that many figures cannot be shown in the Simulink interface. So the value of T1 is 40.61 seconds. The value of Y2 is 1.1548, but again, Simulink interface is not showing the figures. Moving up to the value of T2 is the one in this one is for 41.2675. Both will be used to obtain the value of tau and theta. It will be calculated with the system of the equation shown below. As you can see, when solving the value of tau will be 0.996 and theta will be 40.2079. The process for obtaining the values will be shown below. As you can see, 2 taus over third is minus 0.664. Again, so tau is 0.996 and theta is 4.279. Then we calculate the values of the constant that we obtain using this table. You can see that in tau I, we use theta, and in Kc, we use theta and K, the value what we showed before. For this process, a PI controller can be used. Therefore, the constant will be the following. Kc, again, like I said, using the table, will give us 1978, and tau E will give us 134.2633. Finally, it's important to mention that the values will be defined in Simulink as follows. Yes, in Simulink, the values are different than we use in the formula of the controller. This image shows the use of a PI controller. As you can see, it goes up and then equilibrium. Discussion of the results. Are the performance criteria satisfied? Yes, indeed, the criteria is satisfied because you can see the use of a PI controller in the system using different inputs and outputs. We use the input as the error between the reference temperature, and we can see the output in the oscilloscope. The most valuable thing in this subject, I think, all along the semester was to just see how mathematics can model things, because we can see the automatizations in everywhere. We can see how a first degree system and a second degree system can change everything. Also, we saw Boolean values. These Boolean values help us to understand better complex systems, but the most valuable knowledge is how to think in a mathematical way to model things, because we can see that some input enters to the controller and then some output goes outside, and in the controller or the plant, some mathematical things happens. But now that we can use math, we can predict the output. And this is very important to a lot of things. We can see that with mathematics, everything can be modeled. Well, not everything, but a lot of things. So that will be the most valuable knowledge I have gained during the course. That and that learned I've learned just a little bit more of automatization, that with the Boolean values and with the PI controllers and the PD controllers, I can change and automatize the valve. The lab exercise will have been to me very helpful, and I hope in the future I can go more to the lab to learn more. Thank you.